Have you ever wondered about the creativity it took to thrive in ancient times? A series of underground tunnels, accurately engineered to channel water across vast desert landscapes, or massive underground reservoirs hidden beneath the earth holding thousands of liters of life-sustaining water. Surprised? Well, guess what? There's more. Imagine a place where the landscape is transformed by 16 grand water wheels, arranged in perfect symmetry, powering an ancient factory with nothing but the flow of water. And let's not forget the mesmerizing Stepwells of India, with their 3,500 steps forming a geometric marvel, plunging deep into the earth to retrieve the precious water below. Welcome back to another amazing episode of Forever Green. Today, we're unveiling the secrets of these incredible ancient water technologies that were light years ahead of their time. Click subscribe and let's dive in as we also reveal how windmills were not just charming landscape features, but vital warriors in the ancient battle against the invasion of water. 13. Noria. The Noria, an ancient water lifting device, has been a foundation of hydraulic engineering since its first documented use around the 5th century AD in ancient Syria. Norias are large water wheels that connect the kinetic energy of flowing water to lift water from rivers and streams to higher grounds, typically for irrigation and water supply in agricultural and urban areas. The basic structure of a noria consists of a large, vertical wheel fitted with buckets or compartments around its rim. The wheel is positioned partially submerged in a river or stream. As the current pushes against the paddles or blades at the bottom of the wheel, it rotates, scooping up water into the buckets. As the wheel turns, these buckets are lifted to the top, where the water is then emptied into an aqueduct or storage basin. Norias vary in size, with some over 20 meters high, like Hamas in Syria, lifting thousands of liters per minute, serving large-scale agriculture and populous cities effectively. 12. The Watermills of Barbal. The Watermills of Barbal, located in southern France near the town of Arles, represent an ancient example of industrial-scale water-powered technology. Dating back to the 2nd century AD during Roman Gaul, this complex was one of the most significant and classy of its time, showcasing Roman engineering skills and their ability to connect natural resources for large-scale production. The Barbal complex featured 16 water wheels arranged in 2 parallel rows of 8. These water wheels were powered by a main aqueduct, which was a branch from the main aqueduct that supplied the nearby town of Arles. The force of the water flowing down from the aqueduct turned the wheels, which in turn powered a complex system of gears and millstones. Each pair of water wheels drove a single millstone, grinding wheat and other grains to produce flour, which was a staple of the Roman diet. It's estimated that these mills could produce enough flour to feed the entire population of Arles, which at the time was a significant urban center. Archaeological findings reveal continuous mill operation, showcasing advanced maintenance, engineering, and infrastructure like water channels and flow control mechanisms. 11. Stepwells. The Stepwells of India, known locally as Bauris or Vavs, are an ancient architectural innovation that dates back between 200 and 400 AD. These structures were much more than mere sources of water. They were integral central hubs, serving as gathering places for communities, while beautifully showcasing the artistry and thoughtfulness of ancient Indian engineering. Stepwells are essentially deep, stair-lined wells that allow people to access water by descending multiple levels, sometimes as many as 100 steps or more, to the water table below. The deeper the well, the cooler the retreat, making these places popular for socializing and relaxation during the hot Indian summers. Stepwells, carefully planned for structural integrity and year-round water access, were typically constructed near natural water sources and designed to collect monsoon rainwater. This design ensured a dependable water supply during dry periods and managed drainage to prevent erosion. One of the oldest and largest, the Chand Bauri in Rajasthan, built around 800 AD, features 13 stories and over 3,500 steps in a precise geometrical pattern, descending about 30 meters into the ground. 10. Aqueducts. The Roman aqueducts, beginning around 312 BCE, stand as a witness to the engineering ability of the ancient Romans. These magnificent structures were designed to address one of the most critical challenges of their time, delivering fresh water to rapidly growing urban centers across the Roman Empire. The aqueducts were essentially massive bridge-like structures that covered vast distances, sometimes over hundreds of kilometers, to transport water from distant sources such as lakes and rivers into cities and towns. This engineering feat was achieved through a precise understanding of gradients and gravity, allowing water to flow smoothly across varying terrains without the aid of pumps. Built using stone, brick, and special volcanic cement called putzlana, the aqueducts were constructed to last. They featured a channel, often lined with a waterproof mortar, which sat atop a series of arches. These arches not only supported the weight of the water flowing above, but also allowed for the easy passage of people and animals below. The first Roman aqueduct, Aqua Appia, was built in 312 BCE, followed by others like Aqua Claudia and Anios Novos under Emperor Claudius. Today, the Pont du Gard in southern France stands as a well-preserved iconic example. 9. The hydraulic system of Angkor Wat. The hydraulic system of Angkor Wat, a temple complex in Cambodia built in the 12th century under the reign of King Suryavarman II, represents a monumental achievement in water management and engineering by the Khmer civilization. Angkor Wat's hydraulic system is composed of a series of canals, dams, and reservoirs intricately designed to collect, store, and distribute water throughout the year. Central to this system were the barais, enormous water reservoirs that could hold millions of liters of water. These were essential for irrigation, particularly during the dry season, ensuring that the surrounding fields remained fertile and productive year-round. One of the most significant barais is the West Barai, which measures an impressive 8 kilometers by 2.2 kilometers. This massive reservoir represents the scale and ambition of Angkor Wat's hydraulic engineering. The water from these reservoirs was channeled through a network of canals to various parts of the temple complex and beyond, facilitating not only agriculture, but also maintaining the structural stability of the temple foundations on the soft clay soil of the region. The sophistication of Angkor Wat's hydraulic system is a witness to the advanced understanding of hydrology possessed by the Khmer engineers. 8. The Kharez system in China. The Kharez system in China, much like its counterpart, the Canat in Persia, is an ancient and sophisticated method of water management used to provide a reliable water supply in desert areas. Originating thousands of years ago, this technology was particularly developed in the Xinjiang region to facilitate agriculture in one of the driest parts of China. A Kharez system comprises a series of gently sloping underground channels that connect a series of walls to an underground water source. These channels work by tapping into groundwater and allowing it to flow via gravity towards farmland, villages, and towns. The underground nature of the channels is crucial in desert environments, as it significantly reduces water loss due to evaporation, which can be extremely high under the intense sun. The length of a Kharez can vary greatly, with some extending several kilometers. Constructing a carrez involves digging vertical shafts to access water tables, then horizontal tunnels to channel water to the surface. Regularly shaped shafts facilitate material removal and maintenance, and are capped to prevent debris entry and minimize evaporation. 7. The Balafia Mill. The Balafia Mill, a historic water mill located on the Guadalquivir River in Cordoba, Spain, is a prime example of the advanced water engineering practices in medieval Spain. The mill's origins date back to the Islamic period of Al-Andalus, with the existing structure largely developed during the Caliphate of Cordoba in the 10th century. It was during this era that the Balafia Mill was constructed under the direction of Abd al-Rahman II of the Umayyad dynasty, originally designed to grind grain to feed the growing population. This mill was part of a larger system of mills that were strategically placed along the river to connect its flow for various industrial and agricultural purposes. The Balafia Mill in particular was primarily used for grinding grain, which was a staple activity in supporting the local food supply. The Balafia Mill features a distinctive wheel which has an iconic symbol of Cordoba. Unlike most traditional water mills that use vertical wheels, this mill employed a horizontal wheel. The wheel was powered by the strong currents of the Guadalquivir River, which turned the mill's gears and grinding stones. The architecture of the mill was designed not only for function, but also to integrate with the scenic beauty of the river and its surroundings. Today, the Balafia Mill is no longer in active use, but still stands as a cultural and historical landmark. 6. Parac Samudra. The Parac Samudra, often referred to as the Pimburatawa Tank, is a significant and historic reservoir located in Polonnaruwa, Sri Lanka. It stands as an evidence to the advanced ancient hydraulic civilization of Sri Lanka, renowned for its sophisticated water management systems. The reservoir was constructed under the reign of King Parac I during the 12th century, a period marked by a flourish in agricultural and hydraulic advancements. King Parac I, whose reign represented the golden age of Polonnaruwa, adopted the motto, "Not even a little water that comes from the rain must flow into the ocean without being made useful to man." True to his philosophy, he embarked on an ambitious project to enhance the irrigation and agricultural productivity of his kingdom. The Parac Samudra was the centerpiece of these efforts, designed to harness the waters of the Topawiwa, Aramuduwiwa, and the Dumbutuluwiwa, along with other smaller tanks, effectively creating one of the largest irrigation systems of the time. The reservoir, spanning 2,500 hectares and holding 134 million cubic meters of water, comprises 3 interconnected structures. It features a 14-kilometer embankment standing 12 meters high. Fed by the Amban River and smaller streams through an elaborate channel network, this engineering marvel efficiently manages water flow, providing reliable irrigation and mitigating flood and drought impacts. This reflects a sophisticated grasp of hydraulic engineering, emphasizing the strategic control and utilization of water resources. 5. Canat. Around 800 BCE, in the heart of ancient Persia, a groundbreaking technology emerged out of necessity. This technology was the Canat, an ingenious system designed to bring water from underground aquifers in the mountains to the arid plains where water was scarce. The Canat works through a series of underground tunnels that tap into natural water sources, like aquifers, located deep within the mountains. These tunnels were carefully engineered to have a slight slope, allowing water to flow naturally due to gravity across great distances, sometimes up to 70 kilometers. The system starts with a mother well that is deep enough to reach the water table. From this well, a main channel stretches horizontally across the land, surfacing near communities to provide fresh and cool water. The tunnels, about large enough for a person to crawl through, were lined with resistant materials to prevent collapse and ensure a continuous flow of water. Vertical shafts were dug at intervals along the tunnel to provide air and light, making maintenance possible. The Canat first appeared in Iran, a testament to the resourcefulness of ancient Persian engineers who understood their environment and found sustainable ways to thrive within it. Even today, some Canats are still in use, continuously supplying water for more than 1,000 years. 4. The Basilica Cistern. The Basilica Cistern, located in Istanbul, Turkey, is a stunning example of Byzantine engineering and architectural ability. Constructed in the 6th century AD during the reign of Emperor Justinian I, this reservoir is one of several massive underground water reservoirs built to meet the water needs of the ancient city of Constantinople. Covering an area of approximately 9,800 square meters, this reservoir is capable of holding up to 80,000 cubic meters of water. The roof is supported by 336 marble columns, each standing 9 meters tall, arranged in 12 rows of 28 columns. These columns, repurposed from older structures, showcase a variety of Corinthian and Ionic capitals, adding an eclectic and historic flavor to the architecture. The cistern was designed to be filled with water transported from the Belgrade forest, 19 kilometers away, through aqueducts also commissioned by Justinian. The cistern's interior is coated with a thick layer of waterproof hydraulic mortar, ensuring the vast volume of water stored within does not leak into the surrounding soil and structures. The Basilica Cistern features 2 Medusa head sculptures as column bases in its northwest corner, positioned sideways and upside down, sparking curiosity and legends about their origins and purposes. 3. Pukios. The Pukios are a complex system of underground aqueducts that date back to around 500 AD, crafted by the Nazca culture in Peru. This sophisticated network was engineered to access and distribute groundwater across the arid and harsh landscapes of the Nazca Desert, providing a sustainable water source that has lasted through the centuries. Pukios work through a series of carefully constructed underground channels and wells that tap into the underground water sources. These channels guide the water from aquifers to the surface, primarily for irrigation purposes. What makes the Pukios especially remarkable is their design, which incorporates natural filtration systems and air shafts to keep the water fresh and flowing. The entire system spans several kilometers, with the length and complexity of the network tailored to the topography and the hydrological conditions of the region. The construction of the Pukios was a monumental task, requiring detailed knowledge of geology and hydroengineering that was well ahead of its time. The Nazca people, creators of the Pukios, exhibited advanced hydraulic engineering and environmental management skills, relying on collective effort and cooperation to thrive in a harsh environment. 2. Dutch Windmills, 14th century AD. The iconic Dutch windmills, symbols of creativity and flexibility, paint a charming picture of the Netherlands. These windmills, more than just attractive structures dotting the landscape, are marvels of engineering that played a crucial role in shaping Dutch society. Starting in the 14th century, the Dutch began constructing these majestic windmills, which would come to serve as a vital tool in the battle against the harsh invasion of water. Much of the Netherlands lies below sea level, making water management a matter of survival. Here, windmills were not merely structures, but guardians against the rising waters, keeping the land dry and habitable. Each windmill was a feat of engineering. Typically built from sturdy wood and later also in stone, they stood up to 30 meters high with large, broad sails that could catch even the smallest breeze. These sails were connected to a main shaft that drove a gigantic Archimedean screw or a paddle wheel. As the sails turned with the wind, the screw rotated, scooping up water from the lowlands and releasing it into higher water courses or directly into the sea, thus preventing the flooding of agricultural land and villages. One of the most famous windmill sites is Kinderdijk, a village that boasts 19 well-preserved windmills dating from the 1740s. Number 1. The Yak Cha. The Yak Cha, an ancient Persian ice pit, is a witness to early engineering brilliance, especially attractive given its emergence around 400 BC in the harsh desert climates of what is now Iran. This structure was not just about storing ice, it was about making it, right in the middle of the desert. The temperature inside a Yak Cha could be substantially cooler than the outside environment, particularly impressive considering the desert temperatures could exceed 40 degrees Celsius or 104 degrees Fahrenheit during the day. Inside the Yak Cha, the temperature would remain near or below freezing due to its thick insulated walls and the evaporation cooling process. This allowed ice and stored perishables to remain frozen or cool even through the hot months. Imagine a large dome-shaped building that stands about 18 to 30 feet high, constructed with thick walls made from a special mixture known as sarouge. This mixture included sand, clay, egg whites, lime, goat hair, and ash, ingredients chosen for their insulating properties to keep the inside cool even when the outside temperatures soared. Water from nearby aqueducts was directed into shallow pools where it froze during cooler nights. The ice was then collected and stored in the Yak Cha's deep underground space, insulated by its high dome and thick walls, keeping it cool even in the summer. Well, that's gonna be it for today. If you enjoyed this, make sure to like, subscribe, and hit that bell for more amazing episodes from Forever Green. Thanks for watching, and we'll see you next time.